So to know whether this is actually the case, what you just have to do is that you take your calculator, you press log 3 base 2 plus log 4 base 2. And then you check whether the answer is actually the same as log 12 base 2. And the answer for log 12 base 2 is 3.5849625501. And when you press log 3 base 2 plus log 4 base 2, you equally get 3.5849625501. So since this is the case for both the left and right hand side, this tells us that the equation we just wrote is actually correct, and that log 3 base 2 plus log 4 base 2 is actually equal to 3.58, and the decimal just continue like that. So this is what we call the addition of logarithms. We are about to look at the subtraction of logarithms. So you can pause the video over here, and then you can pause the video over here, and then you write this one. Okay, good. Okay, so using this same understanding, we are about to look at a situation whereby we are going to divide the indices we have here. Okay, so that's what we are going to do. So what if we rather had equation 1 divided by equation 2? Okay, equation 1 divided by equation 2, and this is going to be a exponent n, which is for equation 1 over a exponent n. Okay, so this is going to be equal to k over y. Okay, now let's continue from here. So from indices, we learned that we have to subtract the exponents whenever they are divided, right? So that's what we are going to do. We have a exponent n minus n when we subtract to be equal to k over y. So from the definition of logarithm that we learned, we are going to apply the same understanding over here. Okay? That this is actually going to be equal to the log of k over y to the base a to be equal to n minus n. So from the definition of logarithm, this indices is equal to log of k over y to the base a to be equal to n minus n. Now we know m from here to be equal to log k a, right? Log k base a. So log k over y to the base a is equal to log k base a minus log y base a to the base a. Okay, so minus log y to the base a. So this is what we do when we are subtracting logarithms. Logarithms can actually have several bases. You can have logarithm in base 2, base 3, base 4, and all that is. But then the base of the logarithm can be greater than 1, as I always said. Okay? So base can't be greater. Okay, the base can be, okay, so that 1. I'm coming. It should rather always be greater than 1. That's what it should mean. So the base of a logarithm should always be greater than 1. Okay, that's one thing we should always take note of. So this is also fine. Let's take a simple example on this. What this means is that we have something like log, maybe log 8 over 4 to base 2. This is the same as log 8 to the base 2 minus log 4 to the base 2. So to know whether this is the case, just take a calculator and then you press this, okay? So let's press that. So we have log 8 to the base 2 plus log 4 to the base 2. So we are getting this to be equal to 5. Okay, log 8 to the base 2. Sorry, it's rather minus. Okay, minus. So this is equal to 1. Okay, so when you press log 8 over 4 also to the base 2, you are actually going to get 1. So it means that this is also correct. That's good. That's good. So I'm going to claim this, then we move on. There are a few other things that we have to always take care of, or we have to always take note of whenever we are solving questions on logarithm. So let's look at them. If we have the logarithm of x with an exponent of n to the base of a, this is always equal to n log x to the base a. This one we should take note of, that logarithm of x with the exponent of n to the base a is always equal to n log x to the base a. Also, the log of any number to the same base of that number is equal to 1. That's something we should always take note of. An example we can have is maybe log 4 base 4 is the same as log 2 base 2 is also the same as log 10 base 10. So the log of any number to the same base is always equal to 1. Let's look at number 3. The log of 1 to any base at all is always equal to 0. The log of 1 to any base at all is always equal to 0. So that's also another thing we have to take note of. Now, the last thing we'll be looking at is how to change base. How to change base in logarithm. Because usually you can add or subtract two logarithms very easily if they have the same base. If they do not have the same base, it's very difficult to do that manually. So if they do not have the same base, it's possible for you to be able to change the base. So let's see how we can change the base of the logarithm. Let's say we have something like log of 5 to the base 3. Log 5 to the base 3. We want to change it from base 3 to, let's say, base 2. So it's very easy. What we just do is that you draw a division line, you write a logarithm at the top, logarithm below. So the log of the number that we're looking for will be at the top, then the base will be below, and then the base you want to convert it to will also be written here. So that's all. So log 5 to the base 3, if you want to convert log 5 to the base 3 to base 2, is the same as log 5 to the base 2 divided by log 3 to the base 2. So to base 2. Okay, so this is the case. So to know whether this is actually true, you just press log 5 to the base 3 on your calculator, and then you find the answer. So this is 1.46497.3, and a lot of numbers after the decimal point. Let's also press this and see. That's log 5 to the base 2 divided by log 3 to the base 2. 3 to the base 2. That's the same thing. That's the same 1.46497352. There's so many numbers. So whenever you want to change from one base to the other, this is the approach we always use. Okay. So let's write the general form of the change of base. Let's write that in the corner over here. So let's say we have log b to the base a. We want to change from base a to base maybe c. So we are writing the general form of the change of base. So it will be log. So you write the logarithm of the number at the top, you write the base below, then you write the base you want to change to. So this is the answer for that. Okay? Okay, so we're actually going to take a few questions on this and then we see what we are going to do. Okay, let's consider something like this. So I would like you to pause the video over here and then you write whatever you can write and then we move on from there. Okay, let's take one question and try. Let's try one question. Okay, so log to the base 10 x squared plus 1 minus 2 x equals 1. Okay, so it is also in base 10. One thing we also need to take note of that whenever you have logarithm of a number and then there's no base written there, the base there is actually base 10. That's one thing we always have to take note of. We also have a special type of logarithm to the base e. And then we call this type of logarithm natural logarithm. So a special type of logarithm to the base e is called natural logarithm. E is actually an irrational constant. An irrational constant, which was discovered by one mathematician called Leonard Euler. He's the one who actually discovered this E. And the E has a value of 2.718 and so many other numbers after the decimal point. So you have to take note of that. Okay? Okay, so let's try this question. Okay, so let's try this, okay? Good. So the first thing we have to do here is that we have to take these two from here and then we make it the exponent of the x, okay? So that's one thing that you have to do first and foremost. So minus log x squared to the base 10 equal 1. Now, since it's subtracting, we are going to divide. Okay, so we have log to the base 10, x squared plus 1 and x squared to be equal to 1. Now, from the definition of logarithm, if we have something like this and they want to convert this to indices, what we just do is that we make this to become the exponent of the base 10. So 10, we make the 1 to become the exponent of 10, and then it's going to be equal to x squared plus 1 over x squared. Now we have a quadratic equation which we can easily solve from here. So let's go ahead and solve our quadratic equation. We can cross multiply. So 1 times this is the same thing, x squared plus 1 to be equal to 10x squared. Let's send all of this to that side. So we are going to get 10x squared minus x squared minus 1 equals 0. Okay, so let's continue from there. So 10 minus 1 is the same as 9 x squared minus 1 to be equal to 0. Okay, 9 can also be written in base 3 as 3 squared x squared minus 1 equals 0. This can be 3x all squared minus 1. But 1 can also be written as 1 squared, right? Equals 0. Now, when we have something like this, we call this difference of 2 squares. Okay, difference of 2 squares. So if you have, I can write here, let me just write it here. If you have something like a plus b, a minus b, the answer is always a squared minus b squared. So you should take note of this. So that's the same idea we are going to apply over here. So you are going to get 3x plus 1, 3x minus 1 equals 0. So we'll just solve them from there. So if you take the first bracket, 3x plus 1 equals 0, you have 3x to be equal to minus 1, x is giving us minus 1 and 3. If you take the second one, we have 3x minus 1 equals 0, 3x equals 1, x is equal to 1 and 3. Therefore, the values of x we have from here, x is equal to 1 over 3 or minus 1 over 3. In other words, we can say x is equal to plus or minus 1 over 3. So we have two values of x from here. Okay, so we'll solve one question on this one. We're going to go quickly to the logarithm table. So you can pause the video over here, and then you write what you want to write from here. And then we'll look at the logarithm table. We'll actually take one question on the logarithm table. You know, since medieval times, during those times that there were no calculators, there was something we call the logarithm table. So the logarithm table was what was used to calculate values of logarithm during those times, the 15th centuries and the other centuries. So this logarithm table was actually first produced by Henry Briggs, okay, who was also one amazing mathematician and scientist. And we want to look at this, and then we see how they solved questions on the logarithm table. We'll just pick one question on that. Okay, so let's see something like this. So you can be told to solve something like this without using tables or calculators. You can be told to solve this. So you have to solve 0.00127 over 53.1 without using tables or calculators. So let's see how we're actually going to solve something like this. So the first thing we have to do is that we have to draw a table. So we draw a table of the number, then the logarithm of the number. Okay, so let's take the first number, that's at the numerator. That's 0.00127. So what we do here is that if we have 0.00127, we have something we call the mantissa and then the characteristic. Okay, the mantissa, and then the characteristics. Okay, the mantissa and the, so that's what we are going to use here. So first of all, we have to convert, when the number begins with 0, we convert it to standard form. So standard form simply means that we bring this decimal place to the first non-zero number, which is 1, okay, between the first and second non-zero number. So we have 1.27 times 10 exponents. So let's see how many times the decimal point is actually going across. So we have 1, 2, 3. So that will be 10 exponents, negative 3. Whenever the decimal point is going to the right, it has a negative exponent. If it's going to the left, it has a positive exponent. So when we write it like this, we call this negative 3 the characteristic. Okay, we call the negative, whether it's a negative or it can be either a negative or positive exponent, but it's called the characteristic. Okay, so we write this as bar 3. Okay, so we write the negative 3 as bar 3. So we write a 3 with the negative at the top like that. Then we go and find the logarithm of this side. So the logarithm of this number is what we call the mantissa. Okay, so let's find the logarithm of 1.27. So we find the logarithm of 1.27. That is 0.0. So let's round this off to, let's say, 4 decimal places. So 0.1038. So this is the answer for that. And these readings that we are doing here, we are actually using the logarithm table. We are not using calculators. So at that time, they read these values from the table, from the logarithm table. So you read the log of 1.27 from the logarithm table, then you write the bar 3 over here. Okay. Now, if we have something like this, if we have something like bar 3.1038, this means negative 3 but plus 0.1038. So that's what it means. And this is actually different from negative 3 point this, because negative 3.1038 equals negative 3 minus the decimal point. But then if you write it like bar 3 this way, it means plus the decimal point. So that's one thing you have to really take note of. So we are done with this side. For the denominator, you are just going to find the logarithm of 53.1. So the logarithm of 53.1. So 53.1 is the number. And then the logarithm is 1.72. Let's round it up to 5 decimal places, to 4 decimal places. So this will be the answer to 4 decimal places. So what we are going to do here is that since they are dividing, we are actually going to subtract. We call this equation 1, we call this equation 2. So let's say equation 1 minus equation 2. So we'll subtract equation 2 from equation 1. And let's see how we are actually going to do that. So over here, we have 8 minus 1. Is that possible? 8 minus 1. So yes, we can actually take 1 from 8 and we are going to get 7, right? Good. So 3 minus 5, that's actually not possible. So we have to go and borrow 1. But the 0 doesn't have a 1, so we have to come to this one. So this one will give us a 1, which will become 10 here. And we also take 1 from the 10, which will become 10 here. So this will be left with 9. So 10 plus 3 is 13. 13 minus 5, that is 8.